Right now, an intense heat wave is moving toward the central and eastern United States ahead of July 4th weekend. Meteorologists saw it coming days in advance. But here is the part that almost no one is talking about. The AI systems that were supposed to revolutionize weather forecasting, the ones built by Google, by Nvidia, by Huawei, cannot reliably predict the specific neighborhoods that will hit lethal temperatures until the window to act has already closed. Not by hours, sometimes by days. In 2022, a heat wave in India killed more than 90 people in a single week, and the AI models used to forecast it placed peak temperatures more than 40 kilometers from where the worst deaths actually occurred. The tools exist. The satellite data exists. And people are still dying preventably. That gap between the promise of artificial intelligence and the brutal reality of heat mortality is what this video is about. Heat is the deadliest weather event on Earth. Not hurricanes, not tornadoes, not floods. Heat. The World Health Organization estimates that more than 166,000 people died from heat exposure between 2000 and 2019. In the summer of 2022 alone, a single European heat wave killed more than 61,000 people across the continent. Germany recorded a temperature of 41.7 degrees Celsius, a national record, and the WHO chief, Tedros Adhanom Ghebreyesus, said explicitly that Europe was not prepared. That warning was issued, and then it was mostly forgotten until the next heat wave arrived. This matters to you right now because the United States is entering what climate scientists call a hyperactive heat period. The National Oceanic and Atmospheric Administration projects that by 2030, extreme heat events that once occurred once every 50 years will occur roughly every 5 years. That is not a distant forecast. 2030 is 4 years away. The cities most at risk are not all desert cities. Philadelphia, Chicago, St. Louis, and Louisville consistently rank among the deadliest in heat mortality statistics, largely because their aging housing stock lacks central air conditioning and their populations include a high proportion of elderly residents living alone. In Louisville, during a heat event in 2012, the city's 911 system received more than 1,800 heat-related calls in a single 48-hour window. The second implication is economic. Heat already costs the United States approximately $100 billion annually in reduced labor productivity, according to research published in Nature Communications. Construction workers, agricultural laborers, and outdoor service workers absorb the brunt. A study from the Adrian Arsht Rockefeller Foundation Resilience Center found that extreme heat costs the global economy around $600 billion each year in lost work hours alone. If AI forecasting cannot reliably tell city planners which blocks will hit dangerous temperatures 3 days in advance, those planners cannot deploy cooling buses, open shelters, or make targeted wellness checks in time. The cost of getting it wrong is measured in both dollars and lives, and right now, we are getting it wrong regularly. To understand why AI struggles with heat, you need to understand how traditional weather forecasting was built and what it was never designed to do. For most of the 20th century, weather prediction ran on a system called numerical weather prediction, or NWP. The basic idea is straightforward. You measure the atmosphere at thousands of points around the globe, temperature, pressure, humidity, wind speed, and then you run those measurements through equations based on the laws of physics to simulate how the atmosphere will evolve over time. The European Center for Medium-Range Weather Forecasts, known as ECMWF, built the gold standard of these models. Their system runs on one of the most powerful supercomputers in the world and produces forecasts that are genuinely impressive at the global scale. The problem is resolution. Traditional NWP models divide the Earth's surface into a grid. Until very recently, each cell in that grid was roughly 9 kilometers across. Think of it like a photograph taken on a phone from 2008. You can see the broad shapes, the general outlines, but you cannot read the street signs. A heat wave that kills people in a specific low-income neighborhood, where there is no tree cover and the streets are paved in dark asphalt, will look almost identical, at 9-kilometer resolution, to the affluent neighborhood 2 miles away with mature trees and green parks. But those two neighborhoods can differ by 8 to 12 degrees Celsius during peak heat. That is not a rounding error. That is the difference between discomfort and death. When AI entered weather forecasting, the expectation was that machine learning would solve the resolution problem once and for all. And in some important ways, it has exceeded what anyone thought possible. Google DeepMind released a model called GraphCast in late 2023. Tested against 10 years of historical weather data, GraphCast outperformed the ECMWF's flagship model on 90% of forecast variables and did it in under 60 seconds on a single computer rather than the hours of supercomputer time traditional models require. Huawei released Panga Weather, which showed similarly remarkable accuracy on medium-range forecasting. Nvidia followed with ForecastNet. These are not toy models. They represent a genuine scientific leap, and the meteorological community has taken them seriously. Here is the finding that most people outside of climate science do not know. These models were trained on reanalysis data, specifically a dataset called ERA5, produced by the ECMWF. ERA5 is extraordinary. It covers the entire globe from 1940 to the present, harmonized and quality controlled. But ERA5 itself is gridded at roughly 31 kilometers of resolution. When you train an AI on data that has never seen the difference between a concrete parking lot and a city park, the AI cannot learn to predict that difference. It is like training a doctor entirely on blurry X-rays and then asking them to diagnose conditions that only show up in high-resolution scans. The tool is powerful, but it was shaped by the limits of the data it learned from. And those limits fall hardest on the people who live in urban heat islands, the low-income, the elderly, the unhoused, precisely the communities that need precise, timely warnings the most. The second revelation goes deeper, and it overturns something that most people assume about how AI forecasting actually works. The common assumption is that AI is bad at short-range prediction and improves as the time horizon extends, that it's good at telling you what next week looks like, but unreliable for tomorrow. With heat waves, the opposite is true, and the reason is rooted in the physics of what makes heat waves deadly. A heat wave is not just high temperature. What kills people is the combination of high temperature with high overnight lows. When nighttime temperatures stay above 25 degrees Celsius, what researchers call a tropical night, the human body cannot recover. Core body temperature stays elevated. By the third or fourth consecutive tropical night, even healthy adults begin experiencing physiological stress. The elderly and the very young can go into heat stroke without ever going outdoors. In the 1995 Chicago heat wave, which killed 739 people in 5 days, the overnight low on the worst night was 27 degrees Celsius. That number sealed the death toll more than the daytime peak did. AI models are tested almost exclusively on daytime peak temperature accuracy. The benchmarks used to evaluate GraphCast, Panga Weather, and ForecastNet all emphasize 500 hectopascal geopotential height, a measure relevant to storm tracking, and 2-meter maximum air temperature. Overnight low temperature in dense urban environments is measured separately, treated as secondary, and rarely weighted in model validation. A 2024 study in Geophysical Research Letters found that leading AI weather models underestimated overnight urban low temperatures by an average of 2.3 degrees Celsius. That gap sounds small. Applied across a heat wave with 5 consecutive nights, it means the model is telling emergency managers the nights are survivable when they are not. Now let's get into the actual mechanism, how AI weather models work under the hood, because understanding the failure requires understanding the architecture. Traditional physics-based models simulate the atmosphere from the ground up, using equations that represent fluid dynamics, thermodynamics, and radiative transfer. They are slow because they are solving millions of equations simultaneously at each time step. AI weather models take a fundamentally different approach. They learn patterns. You feed the model the state of the atmosphere at time 0, temperature, wind, pressure, humidity across the entire globe, and you train it to predict the state of the atmosphere at time plus 6 hours, or time plus 12 hours. You do this across decades of historical data until the model becomes very good at recognizing which atmospheric configurations reliably lead to which outcomes. It is not simulating physics. It is recognizing fingerprints. Think of it like a chess engine that does not calculate every possible move from first principles, but instead recognizes board configurations it has seen thousands of times before and knows statistically what follows. This architecture is breathtakingly fast and impressively accurate for the patterns it has seen. The counterintuitive problem is that heat waves, particularly the deadliest ones, are by definition rare. The most extreme heat events are outliers in the training data. A model that has seen 80 years of weather data has seen perhaps a dozen events as extreme as the 2021 Pacific Northwest heat dome, which pushed temperatures in Portland, Oregon to 46.7 degrees Celsius, a temperature that would have seemed physically impossible to most climatologists before it happened. When the model encounters a new configuration that resembles, but does not exactly match, its training fingerprints, it tends to regress toward the mean. It predicts something severe, but not historic. It underestimates. And with heat, underestimating by 3 degrees Celsius does not mean a slightly uncomfortable forecast. It means the cooling centers stay closed and the vulnerable population stays home. The limitations do not stop at architecture. There are harder, more structural problems that are worth being direct about. The first is the urban heat island effect. Cities are hotter than their surrounding areas because of the concentration of dark surfaces, waste heat from air conditioners, reduced vegetation, and the geometry of buildings that trap heat and block wind. The intensity of this effect varies block by block. A park, a river, a stretch of parking lots. Each produces a different microclimate. To model these variations, you need hyper-high-resolution sensor networks embedded throughout the city. Most cities do not have them. New York City has roughly one official weather monitoring station per 30 square kilometers. Houston has worse coverage. Without granular ground truth data, even a perfect AI cannot be trained on a reality it has never observed. The second complication is a political and institutional one. The agencies that own the best atmospheric data, NOAA, ECMWF, the Japan Meteorological Agency, operate under funding models that were not designed for real-time AI integration. NOAA's budget was proposed for significant cuts in 2025. When you reduce the density of weather balloon launches and ocean buoy networks, you degrade the input data that feeds both traditional and AI models. You cannot compensate for fewer observations by adding more computing power. Garbage in, garbage out applies to machine learning with the same unforgiving logic it applies to everything else. This affects your life in specific, concrete ways, and the timeline is shorter than most people realize. If you live in a city with a population over 500,000, your local emergency management office almost certainly uses a commercial weather service that now incorporates AI forecasting as part of its product suite. The decisions those services make about when to issue excessive heat warnings directly influence when your city opens cooling centers, when outdoor construction is halted, and when schools cancel outdoor activities. If the model is systematically underestimating overnight lows by 2 degrees Celsius, and your city's heat emergency threshold is set at a specific overnight minimum, the warning may simply not trigger, even when the physiological risk is already present. If you work in public health, urban planning, civil engineering, or emergency management, the gap between AI marketing and AI performance on hyperlocal heat prediction is something your field needs to reckon with in the next 2 to 3 years. The tools are coming, higher resolution training datasets are being built, and a collaboration between NASA and the private firm Tomorrow.io is developing urban-scale AI forecasting at 500-meter resolution, a step-change improvement over anything currently deployed. But those tools are not here yet, and the heat waves are not waiting. If you are an individual living in an older city building without central air, the actionable reality